No, we were downtown at Madtown reminiscing about it, and I'll lead you to that. Okay, as Gary said, this is the Bruns's house, or used to be the Bruns's house, because now they have moved out to the country. But I am the cat with 9 lives. I keep proving it every single year. So some year I'll run out of my lives. But when I was painting the Bruns's house, I had to get like way up here with my ladder to paint this stuff up here. Kind of hard to do, right? Okay, so how could I do that? Well, I put up a scaffolding like this, and then put the ladder on top of the scaffolding. And then I could paint up here. No problem, right? Until you think about physics. Let's look at physics of this. Let's take the side view from this side looking at this. See any problems with this?
No.
As I'm standing here on the ladder, happy with my paintbrush in my hand, there is force downward, but there is also force what other way? Outward this way. What would happen to the scaffolding if there's too much force this way? Not slide right off the roof. It's going to tip over. And Mr. Birschbach goes falling down on top of this roof. True events, true events. Absolutely true events. What? I didn't break myself.
You did. You had like a broken finger.
No, that's this summer. That story's coming up yet. This has been many years ago. Okay. So Mr. Birschbach lands on the house, the roof here, fairly hard. And this is by Flynn Field, if you know where the house is. This is by Flynn Field. Well, there's a little park just on the south side of Flynn Field with a picnic table and some slides and stuff, whatever. Well, there's a lady sitting at the picnic table reading a book. And crash, crash, bang, bang, this all goes awry. She looks up from her book, sees that I'm not dead, and goes back to reading her book. Doesn't walk over to see if I'm all right, nothing like that. Looks up, see if I'm all right. I kind of, get up and go, whew. And then she goes back immediately reading her book again. So like, okay, whatever. So then what I do is I take the scaffolding, and it's a multi-level scaffolding. I set it at its lowest level, make the ladder extend further, and then I go back to painting again. What's amazing is I didn't break one of these windows when everything went crash and boom down. Okay, so what is related rates? Well, related rates is like, as this goes this way, how fast does this go this way? Okay, that's what related rates is. But we don't want to get to that. We want Mr. Birschbach's stories some more, don't we? Okay, Mr. Birschbach's fails. Here's another Mr. Birschbach fail. There's a branch sticking out of a tree like this, a leafy branch like this. And I'm going to saw this off because this is hitting a house, rubbing up against a house. So I set my ladder up like this against this side, and I saw right here. No problems, right? I should just be able to saw this off, this falls down, and we're all good. Well, what happens is, and this is a little fat, it was more like this. What happens when I cut a big chunk off of this? What will happen to this limb right here? For every force, there's an equal and opposite force type of thing. It's not exactly the way you would state this here. But when this weight goes off, this snaps up. So when this snaps up, Mr. Bierschbach on the ladder with a running chainsaw in his hand, what happens? No, Mr. Bierschbach goes down with the chainsaw still running in his hand, held out like this as he hits the ground. So that is another one of my Mr. Bierschbach fails. What?
That is so embarrassing. I would just lay there and be like, no
Oh.
way, I just fell.
Yeah, that's basically what I did. Okay. You want another one?
Yeah.
All right, here's another one.
Is there 9 of them?
No, there's not 9 of them.
Well, that only makes sense, I think. You need a different type of one.
Well, I haven't used up all my 9. I haven't used up all my 9 lives yet, though.
You're a cat?
I am a cat.
No, there's only one cat here, and it is called Kitty Cat Gatito. Yep. Title's already taken. Yeah.
Who's got the cat?
Kitty Cat Caitlin. Duh. Her literal nickname is Gatito.
Oh, really?
Kitty. Or Gatito Gato.
Okay, 2-story house. I've got to paint above this window somehow.
That is a very good drawing. Yeah, it is compared to your other ones.
So I can't put the ladder up against this wall because there's a roof line coming down that meets right at the edge here. So I got to put the ladder up like this against the house. Well, physics, I'm not very good at physics. That's why Mr. Hodgen is the physics teacher, not me. But once you stand up here, I'm still happy because I'm still standing on the ladder. Once you stand up here on the ladder, what's going to happen to the bottom of the ladder? It's going to go out like this, right? Well, Mr. Bierschbach is painting above the window, and all of a sudden I feel the bottom of the ladder go out. So I grab on to the eaves trough right here and basically go hand over hand until I get to this part of the roof, so then I can drop myself down and get down off the roof.
I would have laughed at you. That is terrible. Why did the ladder go out? I don't get it.
Because, okay, so physics of this. We'll go like this. Okay, so if I'm standing here, my weight is below the fulcrum and the ladder stays against the house. But once I come up here, the weight, it'll go like this. And and I was so far up that I didn't know what was going to happen, so I grabbed onto the eaves trough and the ladder went like that. So I have nothing below me because it's a roof of a house and I'm my impending death. So I go hand over hand till I get close enough to the roof so I can drop down. And then get on the roof and then shimmy myself down and then hang off that roof and drop to the ground. You would think after those 3 experiences I would learn my lesson.
There's more.
But then there was this summer. Okay. So I'm working on a house. Well, let's just look at this house. Imagine there's a roof straight over here, and there's eaves trough. And I'm taking the eaves trough off the house, and I'm on a step ladder. Okay, a step ladder obviously looks like that with a hinge across here. And I'm up basically on this step, pulling on the eaves trough. Well, as I'm pulling like this, and my body's kind of twisting a little bit. Well, the hinges of the step ladder, like this hinge comes out of this side of the step ladder, which then makes the step ladder basically collapse on itself and crumble, and I fall to the ground, go boom, right on the concrete, and thus I have a finger like this now.
Like me.
Mm-hmm.
I didn't break mine.
Well, mine isn't broken, I don't think. I might have broken like the knuckle a little bit, but I pulled the I tore the tendons in the back of my pinky. So yeah, and Jana Peterson, same thing. So multiple of us had. Yep. Yep. So yeah, those are my ladder fail stories. And so we'll talk about ladder fails today. Today, when we talk about related rates. Okay? So somebody's putting on Christmas lights because their wife keeps badgering them about putting up Christmas lights. So they wait as long as they can, and then all of a sudden it rains and freezes, and the driveway is now icy. But their wife says they have to be up by Thanksgiving, and so it's Thanksgiving break, and I got to get those lights on the house, even though it's icy out. So this didn't happen. My wife never forced me to put up Christmas lights when it's icy out. Disclaimer, okay? It's been recorded that she never made me do this, but I'm just saying, by chance, this is why this would happen. So ladder is on an icy sidewalk. The bottom of the ladder is sliding away from the house at 4 feet per second. How fast is Mr. Bierschbach falling? And Mr. Bierschbach is right up here.
You draw people just like a little kindergartner. You go with the two legs and the belly and the head. It's like brilliant. It's not even a sick person. It's like
it's really a bad person. Yeah. How fast is Mr. Bierschbach falling down if he's at the top of the ladder when it's 20 feet above the ground? Okay. So this is 20 feet up. How fast am I falling down? Okay. So this all deals with right triangles, right? So this is a right triangle no matter if it's like this or if it's like this, right? It's a right triangle, okay? The whole situation is a right triangle. So what's the formula for a right triangle? For the sides of a right triangle? Pythagorean theorem, c squared equals a squared plus b squared. Now, what is c in this case? 25. Will 25 change as the ladder is sliding? No, 25 will stay the same. 25 will never change because it's a 25-foot long ladder. How far I'm up in the air changes. How far I'm away from the edge of the house changes. But this never changes. So 25 squared equals this side squared plus this side squared. Now, it doesn't say how far this is away from the house. Okay? So this is a squared, and this, we'll just say b squared because this is changing. Okay, so let's just leave it like that. So 625 equals a squared plus b squared. Now, to figure out how fast I'm falling, that's a change in something. That's a change in my height or whatever. So change in, you take the first derivative. So let's take the first derivative of this, okay? So 625 equals 2a, or let's make these x's and y's, and this would make more sense. So your x is your horizontal, and your y is your vertical, okay? So 2x, and then we'll go dx dt, because it's the change of x over time, okay? And then this would be 2y dy dt, because it's a change in height over time, okay? So if this is 25 and this is 20 by the Pythagorean theorem, what does this have to be? At the exact second that this is 25, what is this side? Well, 25 squared equals 20 squared plus x squared. So this is 625 equals 400 plus x squared. So x squared equals 225. Take the square root. X equals 15. And actually this is 0, because the first derivative is 625 is 0, right? So when this is 20, this is 15, and we know this is going at 4 feet per second outward. So 0 equals 2 times 15 times 4 plus 2 times 20 times dy dt. So to figure out how fast I'm falling, all we do is solve for dy dt. What's 2 times 15? 30 times 4 is 120 plus 40 dy dt. So if we subtract 120 from each side, negative 120 equals 40 dy dt. Divide by 40, dy dt equals negative 3. So when the ladder starts to slip, I'm going at a negative 3 feet per second. Now, after it slips for a while, when it's 15 feet above the ground, once we go down 5 feet, I should start going faster, right? So let's look at that. So, whoa. If this side is 15, then what will this side be? What? It should be 20, right? Because 15 squared plus 20 squared equals 25 squared. 3, 4, 5 triangle. So 0 equals 2x times 4, 2x, and then this would be 20. Actually, yeah. If this is 15, this is 20. Plus 2 times, now this is 15, when I'm 15 feet above the ground, times dy dt. Okay? So then this is 80 times 4, or 160, plus 30 dy dt. So negative 160 equals 30 dy dt, and divide by 30. Dy dt equals, what's negative 160 divided by 30? 5 and like a third? So at the start, when it first starts slipping, I'm going at negative 3 feet per second. Once I'm 5 feet lower, now I'm going at negative 5 1/3 feet per second down. Okay? So that's related rates. All right, so we have a cylinder. There, I draw a cylinder a little better than I draw people, right, Kate? The radius of a cylinder, the radius of the base of a cylinder is decreasing at the rate of 9 millimeters per hour. and the height of the cylinder is increasing at a rate of 2 millimeters per hour. At a certain instant, t sub 0, the base radius is 8 and the height is 3. What is the rate of change of the surface area at that instant? So what we have to do is write down the surface area of a cylinder formula, which is over there. So you'll need your formulas, and these are not on your formula sheet, okay? So you'll need formulas from like over there. So the surface area of a cylinder is 2 pi r squared plus 2 pi r h, okay? So if we take the first derivative of it, the first derivative of the surface area, what would the first derivative of 2 pi r squared be? 4 pi r, and then it changes over time, so it's dr dt, plus 2 pi r, what's first derivative of h? dh dt, plus h times the first derivative of 2 pi r, which is 2 pi dr dt. I just did the product rule with this. 2 pi r times dh dt plus h times 2 pi r, 2 pi dr dt. Okay. All right. So, what is what? Well, we don't have to actually solve this problem. They're just wondering what these numbers are. The 9 millimeters per hour is how much the radius is decreasing. So that's your dr dt, and it would be -9. Okay? So that's the first derivative of the radius, is -9. The height is increasing at 2 per hour. That's the height change. That's your first derivative of your height. The surface area for this is not given because your base is a solid actual number and your height is an actual number, but your surface area is not given. So it's just not given. Okay, here's another problem involving a right triangle. Shinny-Do was given this problem. A person stands 18 meters east of an intersection and watches a car driving away from the intersection, so it's going this way.
Excuse the interruption. Today is flu shot day, so at this time I will be calling the select students that have participated in this down to the cafeteria to have their flu shot taken. So Tevin and Tyler Thompson, Aiden Bostad, Drake Anderson, Preston Highland, Davis Blankenspoor, Luke Johnson, Brianna Bruns, Willem Martin, and Quinn Fleming. Please report to the cafeteria.
Last year, Mrs. Cradaville's daughter, Sutton, didn't get warned by Jill that she was having her flu shot, and she got a flu shot, and oh my, was she ticked at her mom. So we had a volleyball game that night. She would not look at her mom. She would not talk to her mom. Yeah, that was last year, so I don't know which one it was, but that was kind of funny. All right. So, all right, back to the start again. This person's 18 meters away from the intersection. The car is going this way, and it's driving at a rate of 3 meters per second. So this is what's changing. Okay, this is constant. This is how it's changing. At a certain instant, the angle between this angle between the line of sight and the person at the intersection is 0.7 radians. What's the rate of change of the angle at that instant? Okay, so we're talking about an angle. This is the opposite side. This is the adjacent side. Opposite and adjacent is what function? Tangent. Tangent of y, or tangent of theta, equals the opposite side, y, over the adjacent side of 18. Okay? So, tangent equals y over 18. So you just had to come up with the equation, not solve the equation for that one. Just which equation works. This would be for like the ladder falling down or whatever, or, you know, a squared equals b squared c squared without an angle involved. But when we're talking about an angle, then it becomes a tangent problem. A sphere. Duh. A sphere. Okay, there's a sphere. The radius of the sphere is decreasing at 1 meter per hour. At a certain instant, the radius is 4 meters. What's the rate of change of the volume of the sphere at that instant? Now, what's the volume formula of a sphere? 4/3 pi r cubed. Okay, so you'll have to work with formulas today. You'll have to work with formulas. So there's a cone. The radius of the base of a cone is increasing at a rate of 10 meters per second. The height of the cone is fixed at 6 meters. At a certain instant, the radius is 1 meter. What is the rate of change of the volume of the cone at that instant? What's the volume of a cone formula? One-third pi. So this is the 1/3 pi r squared h. Okay? Volume of a cone. All right, in this equation, we want to find dx dt when x is -6 and dy dt is -3. So 3x squared equals xy. If I know x is -6, how can I figure out what y is? Well, I plug it in the original equation and solve it, because you'll need both x and y to solve this in the end. Okay? So 3 times 36 equals -6y. Divide by -6. Y equals -18. Okay? Then we're going to do the first derivative of this. What's the first derivative of that equation? Well, here we do the power rule, so it's 6x, and then since we're dealing with time, it's 6x dx dt, the first derivative of x with respect to time, equals, this side is the product rule, so it's x times the first derivative of y, which is dy dt, plus y times the first derivative of x, which is dx dt. Now, they want us to find dx dt when x is -3, dy dt is negative, or when x is -6 and dy dt is -3. And we know y must be -18. So 6 times -6 times dx dt equals -6 times -3 plus -18 dx dt. I just fill in these three for everything, and all I'm left with is dx dt.
Interruption again. I have Deborah Meyer, Bailey Meadows, Madeline Morehouse, Ashley Nielsen, Brody Nielsen, Davey Shaw, Jade Wilkins, Logan Costello, Olivia Sims, and Carson Wingle. Please report to the cafeteria.
So I just plug in numbers everywhere I can in the equation, and then I'm just left with dx dt, and that's what I solve for. So negative 36 dx dt equals 18 minus 18 dx dt. So if I move this negative 18 over, I'm at negative 18 dx dt equals 18. If I divide by a negative 18, dx dt equals negative 1. So I found dx dt. So in this one, I want to find dx dt when y equals 0.2. So I got to figure out what x is first. So 1 divided by 0.2 equals 8 minus x. What's 1 divided by 0.2? 1 divided by 1/5 is 5. So x must equal 3. Now we got to do the first derivative of this. Well, the first derivative of 1 over y, this is really y to the negative 1 power, right? So it's negative 1 y to the negative second equals 0 minus, oh, and I forgot a dy dt here, equals negative dx dt. Because the first derivative of 8 is 0, the first derivative of x is dx dt. So, negative 1 over y squared times dy dt equals negative dx dt. And I want to find dx dt, so then I just plug in. Y is 0.2, so negative 1 over 0.2 squared times negative 0.5 equals a negative dx dt. This is 0.2 squared is 0.04, which is 1/25. Negative 1 over 1/25 is negative 25 times negative 0.5. So it's 5 equals negative dx dt. So dx dt equals negative 5. Okay? Starting to get this? Starting to wrap your heads around this? When you take a derivative of a variable, you need a dx dt or dy dt or d whatever letter you're dealing with dt. Okay? All right. If we know y and we know dy dt and we want to find dx dt, what letter do we still need before we start the problem? X. So the sign of negative pi equals negative 5x. What's the sign at over here? 0. So 0 equals negative 5x, so that x must be 0. Okay, now let's take the first derivative of this. First derivative of the sign of y is what? Cosine of y dy dt, because we took the derivative of a y, equals first derivative of negative 5x. negative 5, and since we took the derivative of x, it's dx dt. Okay? So all these derivatives are concerned with time. So we're taking the derivative not with respect to x, not with respect to y, but with respect to time. That's why we always have a t on the bottom. Okay? So the cosine of negative pi times 10 equals negative 5 times dx dt. Cosine of negative pi, what's the cosine of negative pi? Negative 1 times 10 equals negative 5 dx dt. If we divide both sides by a negative 5, dx dt equals 2. Now for the advanced stuff. And Lizzie went, what? I thought that was hard enough the way it was. Okay? Now we're going to actually figure out what the values are. So we got a cube. The side of the cube is decreasing at a rate of 9 millimeters per minute. At a certain instant, the side is 19 millimeters. What's the rate of change of the volume of the cube at that instant? So volume of a cube equals what? What's the volume of a cube? I really don't have it up there, do I? Or do I? The side cubed. So the volume is the side cubed. So the rate of the change of the volume is dV dt. The rate of change of the volume is dV dt because that's the first derivative of the volume. Equals 3s squared times the rate of the change of the side. See how that works? So dV dt equals 3 times, now in this problem, the side of the cube is 19, and it's decreasing at a rate of 9. So this is negative 9. So if you just slap that in your calculator, 3 times 19 squared times negative 9, you should get one of these numbers. Which number do I get? Garrett's making a wild guess at C, but it's A. A square. The length of the side of a square is increasing at 15 millimeters per second. At a certain instant, the side of the length of the square is 22. What's the rate of change of the area of the square? Well, what's the formula for the area of a square? Area equals the side squared.
Excuse interruption. I will now take Courtney Wingle, Hazel Francis, Henry Francis, Daniel Hauser, Kyra Weavy, Remington Rostern, Cannon Huntley, Cole Downs, Carter Downs, and Phoebe Corbin. Please report to the cafeteria.
So the first derivative of the area is what? dA dt. What's the first derivative of this side of the equation? 2s ds dt. So we're looking for the rate of change of the area. So the area equals 2 times the length of the side. At a certain instant, the side is 22. And it's increasing at 15. So it's like 660. The radius of a sphere is decreasing at a rate of 4 centimeters per second. So the radius is going down at 4 centimeters per second. At a certain instant, the radius is 10 centimeters. What's the rate of change of the surface area? So surface area of a sphere is 4 pi r squared. So the derivative of that is d sa dt equals 2 times 4 is 8 pi r dr dt. So at a certain instant, the radius is 10 and the rate of change is -4. So it's 8 pi negative, or 10, and then -4. Well, -4 times 8 is -32 times 10 is -320. So it's -320 pi. So it's knowing how to write down the formula and knowing how to take the first derivative of it. Ooh, this one's a fun one. Two cars are driving towards an intersection in perpendicular directions. The first car's velocity is 10 meters per second. Oops, it's driving towards the intersection at 10 meters per second. The second car's velocity is 6 meters per second. At a certain instant, the first car is 4 meters from the intersection, the second car is 3 meters from the intersection. So this one is 4, this one is 3. Okay? What is the rate of change of the distance between the cars at that instant? Okay? The distance between the cars at that instant is 5, right? What's the rate of change of that? So how is this triangle changing? Well, the distance here is c. So c squared equals a squared plus b squared. So if we do this problem, we have to take the first derivative of everything. So 2c dc dt equals 2a dA dt plus 2b dB dt. All right. Now, we want to find the rate of change of this. So that's the distance in between, that's the rate of change of the distance in between the two cars, because c is the distance in between the two cars. So right now, c is 5. We want to find dc dt. A is here. This is A and this is B in this case. So A is 4, and it's going at a -10, because it's going down at 10, plus 2 times B is 3 times -6.
Rachel Bonner, Hayden Octadal, Braylon Octadal, Sam Nussbaum, Tristan Brown, Caleb Hodges, Molly Ingebrigtsen, Caitlin Crabtree, Lakin Olson, Keisha Paradise, Selma Brown. Please report to the cafeteria.
So 10 dc dt equals -116. So if we divide by 10, we get -11.6. A 29-foot ladder is sliding down a vertical wall and the distance between the top of the ladder and the ground is decreasing at 7 meters per minute. At a certain instant, the bottom of the ladder is 21 feet from the wall. What is the rate of change of the distance between the bottom of the ladder and the wall? So we want dx dt here. So this is x, this is y, and this is c. Now, c squared equals x squared plus y squared in this case. So 2c dc dt equals 2x dx dt plus 2y dy dt. What's the length change of the ladder as it's sliding down the wall of the 29-foot ladder? Is it changing lengths? No, so that is 0. So that's what makes this side 0. X, well, we know it's 21 feet, and we're looking for dx dt. Can we figure out what y is? Well, yeah, using the Pythagorean theorem, 21 squared plus y squared would equal 29 squared, right? So 441 plus y squared equals 841. So y squared must be 400. So y must be 20. And it's going down at a negative 7. So 42 dx dt plus 280 or minus 280. I think that's right, because 40 times 7 is 280. Move the 280 over and divide by 42. I would say it's probably 20/3, because if you divide them each by 7, so divide them each by 14, yeah, 20/3. Okay, let's do one more and call it good for the day. I forget. Oh, I got 2 more. Sorry, 2 more. And we'll call it good for the day. The area of a circle is increasing. Well, come on, draw a circle. That's not a circle. That's a circle. The area of a circle is increasing at a rate of 8 square meters per hour. At a certain instant, the area is 36 pi square meters. What is the rate of the change of circumference? So the circumference equals 2 pi r. So what I have to do is I got to figure out what the radius is and then use it and then find the first derivative of the circumference formula. Okay? And I got to do the first derivative of the area formula too. So we'll put the circumference formula over here. C equals 2 pi r. Because we need the rate of the change of the circumference. So the area formula, dA dt, equals 2 pi r dr dt. That's the rate of the change of the area. At a certain instance, the area of the circle is 36 pi square meters. So what is r going to be at that certain instant? Six. Okay, so doing this, the area of a circle is increasing at a rate of 8 pi square meters. So 8 pi is what the area is increasing, equals 2 pi times 6 times dr dt. So the pi's cancel. So 8 equals 12 dr dt. So dr dt equals 8 divided by 12, or 2/3. So we take the first derivative of the circumference, dc dt equals 2 pi. First derivative of r is dr dt. Well, we figured out dr dt right here. So dc dt equals 2 pi times 2/3, or 4/3 pi. That's the rate of the change of circumference. Finally, surface area of a cube is increasing at a rate of 15 square meters per hour. So surface area of a cube, its formula is 6s squared, because the area of each side is s squared and there's 6 sides. At a certain instant, the surface area is that. What's the rate of change of the volume? Well, the volume of a cube is s cubed. So we have to do the derivative of both of them. Now, at a certain instant, the surface area is 24. So 24 equals 6s squared. So 4 equals s squared. So s must equal 2. So in this problem, s will equal 2. First derivative of this, DSA, dt equals 12s ds dt. So the surface area, at a certain instant, the surface area is 24. The surface area of the cube is increasing at 15 meters per hour. So 15 equals 12 times 2 times ds dt. So 15 equals 24 ds dt divided by 24. So 5 a's equals ds dt. So then over here, dv dt, because we want the change of the volume at an instant, so dv dt equals 3s squared ds dt. We figured out what s was over here. S was 2. And we figured out ds dt was 5a's. So 12 times 5a's is 15 halves, which is choice A. Okay, related rates. Not the easiest thing in the world, but we do this more than once this year. Okay? So it's using your implicit differentiation to solve problems. All right, so we will stop the recording. I'm sure I talked